and subtraction formula. This looks like another set of formula to memorize to pass this mathematics course in your life, things like that. But let me say this. The law of universal gravitation, do you know who declared that law? Isaac Newton, right? And since that moment, the science changed. It's a revolution in human history, right? Yeah, it's an important moment. Then later on, and people study more about small objects like a vibrating object, and that uses sine and cosine. That was my propaganda statement when we enter harmonic motion. How they interact and all that is governed by this formula that I'm about to write down. Therefore, it is the governing mathematical rule of the mechanics of a vibrating world. So it sounds like important things. Um, so to do classical mechanics, you have to memorize the law of universal gravitation. On top of it, you can interpret other phenomena and do that. So to understand, vibrating phenomenon, you probably need to know this one to understand it. All right. So here is the statement. So don't forget. I guess that's what I was trying to say. Don't forget after the course. Sine of something is at s radian. This is a very fundamental result. We have to go back to the unit circle. So angles again, right? S radian and plus t radian. What is this? Can we kind of write down different ways? That's the formula. So here is a unit circle. And I'm going to sketch S angle S radian. S radian is over here. That's S radian. Now next one is not T radian, but on top of the S you go T radian more. That's what the angle here is described, right? So if you go T radian more will be described like this amount of angle is T radian. So do you agree that angle T radian is not in standard position? Standard position must have initial side horizontal, but it's not. So neither of this terminal side is representing T radian in standard position. But this terminal side is representing S radian in standard position. What about this one here? What angle does it represent in terms of standard position? In standard position? T plus S, S plus T. T is not quite sketched correctly here. That's what this one is. So y coordinate, why y coordinate? Why am I talking about y coordinate here? Because sine of S plus T is supposed to be y coordinate. Remember that? So the y coordinate of that is what you're looking at. Is there any way write this one down in terms of x coordinate and y coordinate of angle S and T, and that's the goal. And second formula looks like this. How about cosine? And how about tangent? Although I'm stating tangent formula, we're going to focus more about the sine and cosine. That is the building blocks of periodic motion, so we use that a lot. All right. Every semester, I try something new about when I approach this. Is there a better way to introduce why the formula looks like this? And it's difficult. I have something this semester. It's new. I'm approaching. But basically what I'm saying, it is not easy enough. But so that's going to be called something called matrix explanation. I named it. But later, once we get used to this, I'm going to show you a proof that you understand every bit of it, just like law of cosine. Remember law of cosine? Was like Pythagorean theorem. C squared equals a squared plus b squared. But there are a few more with the cosine. Remember we proved it? Many of you proved it perfectly in the bonus quiz. How do you feel about I'm not asking you to remember all the detail about proof, but you probably understood every bit of the steps in the proof when you do that. All right? Just like that, we're going to do that. But that doesn't mean that you understand why it works like this. And basically what I'm saying is that I don't have a good explanation of why it works like this. But I'm going to try something slightly different this semester. And also, so I like to summarize like this. To me, I've studied a lot of this many years. Beyond this level, um, this is the stage. The fact of the matter is beyond our ability to juggle in our head. You just have to simply accept it, how the mathematics leads to, to whatever the conclusion. All right. So, but we'll try it. But we need to get used to this formula first. So, what I'm saying from now on is just a little idea about how to memorize this formula. So it breaks up like this. Sine and cosine stuck together like this. Sine and cosine multiplied. That's how sine breaks down. Cosine and sine, they stuck together. That's the first layer. This is how the formula looks like. And you see plus in between these two angles, and it preserved that plus sign in here. That's the shape of a sine formula. It is not sine s plus sine t, right? Then angle is distributed in the correct place. S goes there and t goes there. S goes there and t goes there. Like that. Alright? Let's look at cosine. How is a cosine different? Cosine starts with cosine, but they're multiplied to cosine again. That's how it's different. And sine is multiplied to sine. So sine, it mixes sine and cosine in their terms. And cosine doesn't mix sine and cosine. It's just a cosine like that. S goes there, t there, S goes there, t there. Like that. Another weird thing about this cosine is that in between here is a positive sign in there, but it becomes negative. Okay, that's the addition formula. Sine of addition of two angles and cosine of addition of two angles. How about difference, subtraction? There. And then it becomes negative there. And positive became negative, and negative becomes positive. That's the subtraction formula. So like I said, this is the main formula you're going to use for a while, but we're listing the formula. Why not? We're going to list tangent. How does tangent look like? What divided by what? Sine divided by cosine. We already wrote sine and cosine here. So all you have to do is that put that long line and juxtapose it and draw a long horizontal line, and that's it. But they did better. They actually wrote that big quotient only in terms of tangent, tangent, tangent. So tangent looked like sine divided by cosine, right? By dividing both top and denominator and numerator, they were able to get rid of all the cosines from the formula and put it into denominator of each part. So it looks like this. You look at this formula and make this cosine disappear. Then cosine disappeared and cosine disappears, right? And they actually go to denominator. The sine becomes tangent. So sine part, cosine disappeared, sine becomes a tangent. There's a plus. How about this guy here? Cosine disappeared, this sine becomes a tangent. Okay? Same thing happened. Numerate the denominator. There were cosine there, right? They're all divided. And as they do that, so they disappeared. Multiplicatively, cancelled out, becomes 1. And what is the sign here? The cosine in between. Negative, right? Because that's what how the cosine works. So the denominator has this negative thing. And there's a sine, they become just tangent. Tangent S times tangent T. This is known as addition formula of sine, tangent. Do you see what happened if I put a negative in between in here? and that's going to change the sine part negative, this part positive there. All right? Because we're going to do this sine and cosine for a while. Many of you remember about sine and cosine and tend to forget how the tangent looked like. That's all right. We're going to come back to that part later. All right. So I just said that this is going to be something important for the laws of vibrating motion. That's all I said. But I'm going to show you something. What I'm showing you here is the graph of 2 times sine 70. And there's one more term, but this graph is not showing that. First, this is really the motion, remember? This graph is describing this simple one-dimensional motion on here, going up and down. This is called simple harmonic motion, go up and down. What causes this one? Like a spring mass system or tension of a guitar string that causes this type of thing. That's one source of a force. Creates amplitude 2, which is how loud, let's say this is air molecule. I use a certain source of force, so it creates this 2 loudness, and 7, where does that go? Pretty much the frequency, right? If 7 is a bigger frequency, you're going to generate bigger frequency than 5 here, omega. So that's just 2 times sine 70, creating a certain motion. Now I just stop that air molecule and change and apply the slightly different source of the force. This time it's, I think it did move in here. Here. It's got moving up and down more. It's a bigger amplitude. If it is a sound, it's a louder sound. But it's a 5T, the frequency got slower, so it's actually lower pitch, things like that. So that's only the second part. Suppose you have a way to create the first motion and second motion. Now this time, you create all these things at the same time, as if you're plucking 2 strings of the guitar. One string generates a certain motion, source of the force. Another string generates a certain. They all put them together. Weird thing is that these are positions, not forces. To me, adding 2 forces makes perfect sense. I'm applying a certain amount of force to this water bottle. Next person about a certain bottle. If they're pushing it together, of course it adds up. So adding 2 forces make perfect sense. But adding 2 positions, these are representing position, right? Adding 2 positions doesn't make sense to me. But if you study the force and acceleration and all that, you realize that it's okay to add this 2 position. That's going to correctly represent what happened if you add 2 forces in resulting position, right? That's a bit of a stretch, but it is something they have to accept it at this stage. So what's going to happen if I apply this source coming from one plucking string, another plucking string? They're going to vibrate the same molecule in a different way, right? So these looks very handsome and nice like this, but when you combine them together, they look like this. I want you to first pay attention to the motion of this guy, not look at this graph. It is different from simple harmonic motion. It's doing some funny thing in the middle of the way there, right? Jiggling and going back and jiggling and going back. So if you pluck these 2 strings at the same time, the air molecule motion might look like this. So it is all propagating from the actual body of a guitar, if it is a guitar, and it arrives to ear, and there is this tiny thing that vibrates inside your eardrum, right? That signal is just a signal right here. That is going to the brain. The brain does not know if it is 270 and 35T. Only thing it knows is the weird vibration. But whatever happens in our brain, because it's our musical training that you have throughout your year, you be able to distinguish that sounds like A and G, put them together, right? So your brain only receive this one, not this formula here, decomposition, but somewhat you kind of decompose these 2 things nicely. This phenomenon happens again, like sunlight coming from the outer space. It looks just like just white color, but if you make it through the prism, that crystal-shaped thing, and then it reveals, and whiteness of either spectrum shape correspond to the amplitude of the wavelength, and color this correspond to this frequency. So all the composite of light wave coming in and this medium actually nicely separates what's involved in here, what's involved in that thing. I'm going to call in this course, this is quite a standard term, although the book doesn't use it, this 2 times 70 pure wave. And this one is another pure wave. This thing here you're looking at is not pure wave, but it's a sum of a two pure wave. And when you receive it, you don't know what is the sum of what pure wave. So if you can kind of figure out the pure wave that is involved, that would be great. And it's wonderful thing about this thing is in mathematical theory is that there's only one way to do this. Suppose there's a complicated wave, there's no other way than putting these two different pure waves and get this exactly the same wave. There's only one way to do that. So that's decomposition process. Is that called frequency decomposition or spectral decomposition in many other parts of the science? So in this course, we're going to experience a little bit of a baby example of this. You have some sort of periodic motion in there. It is not simply harmonic. And so we're going to decompose it into two different pure waves, simple harmonic motion. And to do that, what are we going to use, you think? Addition and subtraction formula. We're going to just combine and juggle that to figure out which pure waves are involved in this more complicated motion. So that's another application of this addition formula. Right now we're going to do something simple. So I'm hiding it. I want you to go to the next page. So not looking at the formula and use this opportunity to trigger or try to memorize how the formula looks like, rather than just flipping it back to see how what the formula is. So where are you? Here is addition formula. All right, the exact value came back. It's because they want you to think about things that are involved in here, not just using the calculator, right? It's not just about getting an answer, it's about how you think about the problems. All right, exact values. How do you get to exact value? What do you need if you don't have a calculator? You're going to draw something, right? What are you going to draw? Unit circle, even more before that? There was this triangle, remember this? And what are the angles here? 45, this is isosceles. What are the numbers around? The shortest one, root 2. Excellent. This is the class that comes out fastest. Excellent. All right, what about this triangle? 60 and 30. What are the numbers? Shortest one, 1, 2, and root 3. These are the exact value we know, right? Now let's read this problem. Cosine 75. None of these are 75, right? So here's how you do it. Cosine of 75. All right, all we have is 45, 60, and 30. Can you combine these angles, that special angles, to get 75? 40 and 30. I agree. I concur. 45 plus 30. Okay? Do you know what to do next? Some formula you learned today? Addition formula. Don't go back. Don't flip back. Just look at that's exactly cosine s plus t. You see that? Cosine s plus t. So don't write down this s plus t. Write down that, with an empty parenthesis. Try to do that. Try to remember the shape of a cosine addition formula. Right? That's a cosine, cosine, sine, sine, and angles just go right there. 45, 30, 45, 30. Good enough? All right, what now? Don't touch your calculator. Cosine 45, where do you go? 45-degree triangle. Here's cosine 30, right? Where do you go? Go to the 30 triangle. And substitute all these 4 factors that is involved by looking at this triangle in here. here is the triangle. Remember cosine 45? What divided by what? Adjacent? Right, adjacent divided by hypotenuse. Okay? That's what we're looking at here. So this is your exercise. Finish it. This thing, calculation. Was that okay? Yeah, this is so you pull out your calculator and hit cosine 75 and compare that value with this square root thing. They're supposed to be exactly the same. And this one is even better, right? It's in the exact form, no decimal. Now we're going to push this idea on further and further. Keep breaking it down. You get down to eventually like cosine of 0.5 degree. By having that, control, you can eventually calculate any cosine value to any precision if you have time and patience. Just keep applying this one and break it down. So I'm sure this is how they got very accurate value of a cosine and sine back then in ancient time that was used for whatever the observation, celestial observation, or whatever they use, exact value. No calculator, but they can still get their hands on like this, breaking it down. We still need more solid idea than just combining these special angles. You will learn that, but I think it shows you some idea. But we can go further than just more than a special angle. Is that okay? So next part is going to be exercise, and I want you to complete it entirely on your own. So the part B is not that. It is changed. It's going to be, this time I want to do sine. Sine pi over 12. Is sine pi over 12 radian? Okay. Yeah, I think it's better so that you can easily see how it's combined from special angles. So convert that angle pi over 12 first to degree, right? Then think about how to combine this 45 and 60, 30 thing to get what you want. So was it okay? Sine, and then you go through, and then it happened to be equal to whatever we just did before. Any question? So let me write this one down as observation from Pat. That's okay. We just did cosine 75, right? And we just did sine of what? 15. And they were equal to each other. Yeah. If I write down like this, cosine 75 and sine 15, you see some nice thing about 75 and 15 together? 90 degree, right? So here it is. Triangle. Like this. What is this angle here? 75, right? What about this one here? 15. So sine 15 will be this guy A here divided by hypotenuse C, right? How about cosine 75? This guy A divided by C. Happen to be the same, right? So you don't need to calculate to show these two things are the same. Just look at the triangle and it's the same. But their values actually turn out the same through the formula. Does that make sense? All right. So next time we're gonna see more of these angles and that decomposition like that. So now this time I'm gonna do a new thing. I'm gonna explain why this thing works like this. All right. And what is it I'm about to do? I'm going to explain a little bit about where this shape of a formula come from. All right. So the explanation I thought about is not self-contained. It's not easy to just understand in what we have so far discussed. So I'm going to go beyond a little bit. Is the idea of a rotation. Here is a unit circle. Actually, it doesn't matter if it's unit circle. So I'm going to explain. I have a random position here, x comma y. Right? Then it has its own distance from here to there. This I label it, I explained, as a matrix explanation. It's not a proof. With gaps, it means there are certain things I'm just going to say it and not really be able to explain it. Alright, I'm going to rotate this x comma y around the origin by angle, let's say theta. I'm going to do angle S here. Then you arrive at somewhere here like that. It keeps the kind of radius there, right? It's the same. And you arrive at here x comma y comma. And if you look at it as a motion, this is going to leave this type of trace. Does that make sense? If you move it like that. The question is that I give you x comma y and I give you s radian, and can you calculate this new coordinate? That is the question first in hand. And it turns out this is the transfer. This application is transfer. Every point is rotated by s radian. It's the transformation. This transformation has interesting properties called linear transformation. It's not really complicated. It's really easy to understand the transformation. That's the part I have to wave my hand. I'm not going to explain it further. So all I want to know is a formula. I want to know formula. So what is the formula? I give you an x comma y, and what is this x prime y prime? This is a matrix algebra. All the linear transformation is explained through matrix algebra. You've seen the movie Matrix, right? In the background, it has a matrix shape in there, although it's kind of drilling down. The two coordinates, they use this matrix. Like this, it's a 2 by 2. You have 2 slots in a column and 2 slots in a row. So altogether, 4 slots of a number going in there. Using the linearity, which is a pretty neat thing, and using the structure of a matrix, you actually get this formula really easily, if you understand this fancy linearity property. Alright, so 4 numbers going in there in the formula. The first number turns out to be cosine s. Second number in the right upper corner turns out to be negative sine t. Lower left corner gets sine t, and lower right corner gets cosine t. So there's this 4 number. We're going to do something with this 4 number to that x comma y to get this coordinates, right? Alright, what are you going to do? You write that x and y right next to it like this. That's the coordinate here. And they put this bracket and multiply these two things like that. If you know what matrix multiplication is, it's going to make perfect sense. If not, I have to explain how these things come about. Matrix multiplication go like this. X go over here and y goes over there. And you multiply x down the road, down the row, and y multiply down the road there. So we get following expressions. 2 by 2. You write cosine s times x. You multiply there, and x there is a sine t times x. Okay? And here you multiply negative sine t times y. Multiply y down there, cosine s times y. And you bracket. Doesn't it still look like a matrix with the different 4 entries? But it is supposed to be this coordinate. So next step you do is that don't look at this as a matrix, but put them really close to each other like that and add them together, whatever the sign preserved. Do you see this is a 1 number? Before it was a 2 separate entries. Now I add them together, it's a number. And down there is number. And that becomes x comma, x prime. That becomes y prime. That is a formula that's coming really easily out of this linearity and matrix algebra. So you have to accept this. X comma y rotated around the origin by s radian. The formula is this cosine s x and blah blah blah. That's the formula. Okay? So I'm going to do it 2 times. You're going to first rotate s radian, right? Then what? To t radian. That's what we're going to do. So here is our picture. Circle. like that. And we're going to go first where? S radian here, right? What is this point here? 1 comma 0, thank you. And so on the unit circle, you go S unit first, S radian first, right? And at that point, we're going to call this one x1, y1. Okay, you arrive it there, and from there, we go T radian more. And then we wonder what that eventual goal and x2, y2 is, right? So what is y2 there in terms of S and T here? Sine coordinate, sine, because y coordinate is a sine, right? Y coordinate is a sine. But what is the angle? Angle is not 1. We first go S and then go T more. S plus T. Isn't that what we wanted to know? Right? How about x2? Cosine of S plus T. Alright? So that's what we wanted to know. What we're going to do is that you use the matrix, go one step at the end of the S radian, and from there we go one more to T radian. So what is the first point? S radian rotation is the first step we're going to do. The point is written vertically like this, 1, 0, right? Now, some of you have this photographic memory of just that matrix I wrote down. Remember, upper left corner, what was it? Cosine S. Right corner, negative sine T. Down here, sine T and cosine T. So, what do we do with this 1, 0? You write 1, 0 up here, right? And multiply down the row, down the column there. So what is it? First one is cosine S. Down there is sine T. We just multiply 1 there, right? How about 0? How convenient. They all knocked out. This is a new point. That point x1, y1 is this one in here. This is x1 and that's y1. And that's dumber. That's because x1 is a cosine S and y1 is a sine S. We already know that, right? But it recovered that. You know just what happened? This is the standard position angle S. x1 is supposed to be cosine S. Sorry about this. This is supposed to be all S in there. Oh, it's a mistake. It's all S. There's no T yet. We didn't rotate T. Sorry about this. It's all S. So if that, then it is of course that. Next step is non-trivial. It really is. We are here, right? So, and the T radian further rotation. Okay? So where are we in the immediate step? Cosine S, right? And the sine S. That's where we are. And we go how many angle more? T angle more. T more. So this is going to be cosine T, negative sine T down here, sine T, cosine T. Now we're going to multiply through and put them together and see what the coordinate you get. Let's do that. So I'm going to put them down. So you write cosine T up there. That's your intermediate x coordinate, and sine S there, right? Multiply down the column. Then what do you get? Cosine S times cosine T. And they're add them together, and let's do that down here first. Sine T times cosine S. How about this one? We have to put right next to it so that we see the whole thing. Sine T times sine S. Down here, cosine T times sine S. Right? That's the final coordinates. These guys are x2 and these guys are y2, right? What is the x2 supposed to be? x2 is supposed to be cosine of S plus T, right? So does it look like cosine of S plus T right there? Haven't you seen that before? What is that called? This formula here. Addition formula? Right? Cosine, cosine, sine, sine? That's the addition formula. It's a cosine of S plus T. That's x2. That's a x coordinate of the terminal point, S plus 2. S plus T in there. How about this guy here? The sign, S and T is mixed up a little bit, but you can rearrange it and get the result. So why did I do this? Is to show you where this, cross multiplication come from. Where this, where they come from. This one matrix multiplied to another 2 times and come about like that. So there's a guy in the street and describe you, asks you, why does it look like this, cross multiply like this? And your short answer is that's how the matrix multiplied out, right? That's how the 2 by 2 matrix is multiplied out. That's why it looked like that. I think it's still dissatisfying because it's not a physical intuition that you get why they mingle together like this. Quantum mechanics is written in terms of complex variables, and this is really the complex algebra, and it is beyond everybody's way to juggle things. So nobody try that. Just obey the law of this mathematics and just deal with it. Don't try to think about it too much. But we got to keep trying. Next semester I'm going to try something even further, see if we can actually use some sort of physical intuition to see if this is really happening. Maybe a few more semesters I'll get really better, but it's a hard part to kind of bring the physical intuition to this formula. But by the end of the session 3, you take this under control and be able to write down. So usually I hand out the test and then everybody just go to their problem that says state the addition formula. Everybody just quickly write down before it disappears, and then of course you have to do that problem based on that formula, right? And there are students who write down wrong formula, and everything else your test is depending on that wrong formula, then you're in terrible situation. So make sure you get this one under control. Like I said, I don't want to give you the formula sheet, just looking at it and plug and chug, nothing like that. Understanding the structure of a formula by just thinking about it like this, it is an important part of understanding spectral decomposition and all the other trigonometric analysis that's coming. Alright? Okay, that was it.